Hello, everyone, and thank you for coming to Sustainable Labs Canada webinar series. I just want to make sure that everybody can hear me and that the chat and everything is working before we begin. Perfect. So this webinar will begin shortly, but before we begin, I just want a reminder that questions will be answered at the end of the webinar. If you have any questions during the presentation, I encourage you to enter them into the Q&A button that's part of the Zoom interface at the bottom. It will save the questions in a place we can review them and address them at the end, and it'll allow other people to upvote questions if we have the same questions. Please note this webinar will also be recorded and will be posted on the SOCAN website so that you can review it later or recommend it to anybody else in your organization. This month, we are pleased to present Sumaya Musazadeh, who will be presenting on value design versus value engineering, making a case for integrated lab planning. Sumaya is a planner and senior designer at HDR, specializing in education, science, and advanced technology projects. Currently, she is leading the planning and design of the York University Neuroscience Facility. Previously, she was a member of IPD design teams for the Canadian Nuclear Labs Project and McMaster Innovation Park. She's authored the value design approach and contributed to the parametric costing and modular planning framework for lab design at HDR. And Sumaya, are you ready to go?
Yes, thanks, Tyler.
Perfect. And please proceed.
Okay, I'm just going to share my screen. Hi, everyone. Thank you for participating, and thanks Sustainable Labs Canada for all the arrangements to make this possible. As a lab user, owner, engineer, or architect, you have perhaps experienced a budget problem in one of your lab projects. At some point, you had to do some sort of value engineering to address the problem, and more likely than not, it involved a compromise. In this session, I want to share a framework that we adopted in our team at HDR to mitigate this issue. The value design framework is based on a highly integrated planning approach that tries to maximize the outcome of your budget and minimize the undesired compromises. Today, I want to begin with the problem, the budget and program misalignment issue that we had in a recent lab project, how we solved it, and why it's now a systematic approach in our studio. Well, we call it value design, or VD. We use the term value a lot in this presentation. Before doing some research about it, my perception was that it's a totally qualitative notion. Well, we'll see that it has a specific definition that can help us to think differently. And next, I talk about the differences of value design and value engineering. And to really understand why we're experiencing this budget misalignment problem, we first need to understand the science and lab trends. And this will help us to understand how integrated planning is addressing the issue. And at the end, I briefly talk about the integrated project delivery method and its principle that we can borrow for other delivery methods. Why think about alternatives to planning and designing lab buildings? A cost estimator told me once, if you're building a lab building, it will cost about $700 to $800 per square foot. Half of it is M&E, another 10 to 15% are for fees. And the frustration for us is how to achieve all the project goals with this remaining 35%, right? We all know where it goes. The initial design is typically over budget because it's hard to fit envelope, fit out equipment and a structure in this kind of remaining 35 to 40% of the budget. Then the entire team needs to go over a painful exercise of value engineering to align the program with the budget. And this process is often the most difficult for the end users and owners, since they should give up not just part of their spatial needs, but also any ambitions that they may have for their project. Well, we had a similar problem with the new neuroscience facility that we are designing for York University here in Toronto. This project is a 3-story facility located beside an existing health research building. It includes wet and dry labs, plus faculty and graduate student offices. The client wanted a special separation between the program blocks, so we organized the building in 3 connected levels with links to existing building at key circulation points. The wet labs are in the lower level, the dry labs and some other public functions are on the main level, and the faculty and graduate students are on the top floor. We decided early to have the mechanical space on the main level sandwiched between the lower and the top floor, and it helped to combine the mechanical room and the interstitial space to do all the labs maintenance from this space. It also eliminated the need for big shafts and some extra plumbing. The overall building design is very energy efficient and sustainable. A pre-grown modular green roof system covers almost 70% of the roof area. As you know, having a certain percentage of green roof is a requirement in the city of Toronto. Our team really maximized it to address the stormwater management requirements as well. And the structure for top 2 floors that are mostly dry lab and offices as mass timber, it helps with the construction speed and makes it possible to expose the structure and eliminate some extra finishes. And of course, it makes it much more attractive and inviting space for the users. When we did our first cost estimate, the project was over budget by roughly about 15%. The initial reaction to that might be to remove some of the features that we just discussed, like mass timber or green roof. And that was our first reaction too, until we did a costing analysis for the project. So the chart here shows how the budget was distributed based on the elemental cost estimate. As you see here, the structure, envelope, and fit out are only 40% of the project. So it turns out that that cost estimator was not wrong. And as I said, the project was over budget by 15%. You can imagine it was very frustrating to find ways to cut 15% out of less than half of the construction budget. For example, even if we had decided not to do mass timber, we would have had to replace it with another system like steel structure and add other finishes such as ceilings for fireproofing. Well, we actually costed this option and it turned out to be a wash, if not more expensive. So basically, no value engineering could get us the savings we needed. Another way to possibly resolve this problem was to reduce building area. And for this building, it translates that 15% translates to almost 7,000 square foot area reduction, which is how we typically exercise value engineering in our industry, right? So this solution is unacceptable for a project of this size. With this, our users would have ended up with less space capacity than their current building. Big compromise, right? So here's what finally worked. A target value design approach. We looked for savings within each discipline based on their share from the total budget. You can see the percentages that each discipline had to save. And this breakdown made the savings much more possible. Then we only needed to cut about 1,800 square foot from the gross building area, which was acceptable to the users. We ask each discipline to find ways to optimize their system to hit the target budget for their scope. And during this process, all the consultants realized that in order to really optimize their system, they had to understand other consultants' solution and look for synergies between their design. And this was the only way to find meaningful optimization without unacceptable compromises. And naturally, it became a very integrated process. Let me tell you about one of the example of this kind of target value design and integrated thinking that really helped the project. And that was the decision to change chill beams for underfloor air distribution. As I mentioned in the previous slides, the building has a different mechanical system for the dry labs and office spaces that are on the top 2 floors. This helps to lower the energy demand. And initially, the mechanical team considered an overhead air distribution using chill beams. For those who are not familiar with chill beams, they are a low energy and low maintenance system. 80% of the supply is recirculated air within the space. The image below on the right show the chill beams in an open office setup. And in this level only, we needed about 100 units for the layout of the 3rd floor that you see here. It's a significant cost. During optimization, our engineer realized because of where the mechanical space is located in our design, an underfloor air distribution with a raised floor plenum may make more sense. It saves the chill beams cost and a significant portion of the associated piping and ducting. And the beauty of this decision was that it brought a lot of value to other aspects of the project. For example, the IT and electrical distribution is a lot easier and cheaper with the raised floor system. The layout all of a sudden becomes much more flexible with the raised floor system, which was an important criteria for our client. And the underfloor air distribution, as many of you know, significantly increases the user comfort. And with the pandemic experience, having the choice to introduce more fresh air to the space, if needed, is a big plus for this alternative. And the underfloor air distribution system is very much compatible with the natural ventilation, and our team is now considering automated operable windows to enhance the indoor air quality even more. And for us, this was about future-proofing the building, something that the team didn't really consider before this target value design exercise. Every discipline was kind of thinking in silos. So I mentioned value. Let's talk about value. We all have an intuitive understanding of it, but in project management, there is a tangible and quantifiable definition for it. The famous value equation defines value as a function, outcome, or benefit over cost. And in this equation, function is a measure of the sort of performance capabilities of the project, and cost is the resources required to achieve that. Of course, one way to increase value is to achieve the same performance at a lower cost. But we all know there is a limit to how much you can lower the cost before compromising the function, or how much you can bargain with the vendors and suppliers over their prices. Another way based on this formula is to increase performance. In other words, buy or get more with the same money. And in reality, we often and naturally do both. We try to get more with less as much as possible. On a typical construction project, this is the budget structure, right? I showed that pie chart before. The project is basically evaluated based on each budget component's value or what each discipline brings to the table. To increase value, we try to maximize each component. Of course, But as I discussed in the project example before, there is a limit to how much efficiency you can get with this approach. Each component can try to be as efficient as it can inside its silo. If we start thinking outside of the silos, then the sum can start to be bigger than the parts. Value design that we're advocating is here is really about not just maximizing each component, but also understand the synergies between them. And by capitalizing on these synergies, we minimize the cost and maximize the gain. In other words, not just we meet the budget, but also exceed the performance. And as you see in the diagram, we're making dependencies now between the discipline, which is impossible to work out unless we really work and plan together for that desired outcome. And this is what we call value design. It might be helpful to talk a little bit about value engineering and how it's different from what we call value design. Many of you might be familiar with this history, but General Electric invented value engineering during World War II because of the war. There was a lot, there were all kinds of raw materials and component shortages. And to ensure the continuity of their production, the engineers at GE looked for acceptable alternative parts in the original design. And during this process, they realized that some of these substitutions achieve the same performance and reduce costs. So they adopted this approach as a technique that they called value engineering. So with something that started as a happy accident, they sort of responded to a crisis and turned it into a systematic approach. Value engineering is about reactively responding to a situation to control costs, whereas value design is kind of proactively planning for the desired outcome. And this value engineering is more of a linear process of switching one product or solution with another, but value design is a non-linear and systematic design thinking to bring harmony to the solutions and budget. Many of you are familiar with this diagram. It shows that there is a cost associated with each saving or change that you do in a project. Naturally, the earlier you plan for savings, it will cost less. The later in the process you make a change, the more expensive applying that change will be. So the sooner you do value analysis, the more benefit you get from it. In our industry, we typically do value engineering in the later phases of the project, like construction documentation or a tender sometimes even. But we can only do value design in the earliest stages of the project, which is that proactive planning to maximize your gain and really plan for it. Value design is not necessarily a substitute for value engineering. If there is a sudden change in the market or another situation, we may still need to value engineer to rectify it. And this value design really requires all the disciplines to work together at the planning stage to identify synergies between their solutions to add value. This is what we call integrated planning. The architects cannot do this alone. Let's look at why we're experiencing this budget misalignment problem to begin with. The reality is that the science and lab trends are rapidly changing. We now see new requirements in the space program that we frankly didn't see even 5 years ago. But the budget structure and our perception of this building typology has not changed much. In the next few slides, we will see how the new trends can benefit from this integrated planning approach. But before that, I wanted to show you this slide. So the problem that I talked about for the York Neuroscience facility was not an isolated incident. We analyzed other lab projects that we had and started to see a similar budget structure and the struggles in these projects. And as you see, for example, the M&E share of the construction budget is more than 30%, often even sometimes 40%. And you see that in some cases, it's even more than the architectural scope. So it will be really a lost cause if the engineers don't actively participate in the planning stage. Well, that's one thing. And the other issue is that this budget structure really doesn't reflect the new and emerging expectations for lab building, which we will review some of these in the next few slides. Traditionally, labs were mainly a place for focused experimentation. That's the image on the left here. You all have seen the shift towards a more team-based environment recently. But if you look at some of the cutting-edge research spaces, the kind of science innovation centers, the look, feel, and function of the labs are very different. So the image on the right here shows an AstraZeneca lab building. As you see, there is a seamless flow between the wet areas, the touchdown spaces, and the offices. We believe this is how most labs will function in the future. These are some of the new performance requirements that we started to see in the recent projects. The labs need to be more flexible, multidisciplinary, accommodate collaboration, and create a sense of community. There is a trend towards more healthy and sustainable labs, which has brought us today, of course. The first trend, adaptability. Labs of the future need to be flexible. For example, even now in the tenant lab buildings, the space needs some rearrangement with every new tenant. So the building and systems need to be adaptable. In addition, with advancement in data science and technology, the trajectory of lab building is a little bit unclear at the moment and hard to design for. So to deal with these uncertainties, flexibility has become an important strategy. Flexibility that I'm talking about here is really about understanding the program at the level of a common building block. How can we achieve this flexibility? The common building block is a unit that can be multiplied like a truly modular system. It's important to make sure that this module works with the structural grid. And on top of that, all the other systems such as ventilation, power, lighting, and plumbing should also be planned and designed the same way to support this idea of modularity and the potential for customization. Doing modular design does not necessarily require additional costs, but not doing it will lead to costly renovations in the future to accommodate change. The next trend is sort of this shift towards more multidisciplinary labs. One implication for the sort of planning team is that there are different personalities in one space with different needs and work styles. Traditionally, we maybe only had a couple of these personas, like the practitioner, some support staff, and lab technicians. But because of things like economic development and industry engagement, we now have new personas in the same building, like managers or leaders. Now, in addition to wet labs, we need spaces to accommodate these other work styles, like enclosed and open offices, even teaching spaces in some cases. And these characters don't work in silos. They need spaces to gather, collide, collaborate, and communicate, both internally and externally. And this trend really signifies a shift from mainly acute lab environment to a more diverse environment with the spaces that have different intensities in terms of mechanical and electrical needs. Next is the trend towards more collaborative environments that support innovation. Many of you know Mars Building in Toronto. It's a high-profile incubator lab building. This building is very popular. There is a long wait list to lease a lab space in this building. And the image on the right is a snapshot from the Mars website. Their message emphasizes the community aspect of their building. And if you have ever been to this building, you don't forget the spacious lobby and the gathering space. It's the image on the left. It's truly a public thoroughfare, a place for exchanging ideas, both at the local level and global science fair kind of scale. It's interesting to know that even now that many buildings are empty of occupants because of the pandemic, this space is turned into a COVID testing and vaccine center, serving the community. And of course, its large volume, proper passive and active ventilation make this kind of use possible. So we see a recent trend in marketing the lab buildings as incubator spaces for innovation and science exchange that attract and retain high-profile organizations, researchers, and technicians. So these buildings need active public spaces for gathering and ideation in addition to, acute lab spaces. The other trend is health and wellness. They've become an important criteria for lab environments recently. The amenity spaces that support wellness are part of the space program now, and they are essential to increase efficiency, attract top researchers, and retain skilled staff. But whenever there is a budget creep, we often see these features get value engineered, which is a significant compromise for the owners and users in the long run. But then the last but not least is this trend towards more sustainable and green labs. We all know that science buildings are blamed for their intensive energy use. There is a lot of pressure to lower the lab's energy consumptions and greenhouse gas emissions. Recent carbon taxes make this even more pressing. And engineers worked really hard to design heat recovery system, incorporate more controls and sensors and other similar technologies to achieve these goals. And this often drives the M&E costs even higher, hence the charts that I showed you earlier. But the real game changer in this discourse is to recognize that the wet lab footprint in the traditional sense is shrinking. The equipment you see in this image on the right does all the clinical lab testing in these fully automated machines in only 20 square foot and in a fraction of time. So the lab technicians are less hands-on and doing the experiment and producing data, and doing more of analyzing them, which really what I think our brain should do. So, and this technology is already in the market and is being used for COVID testing. So the chemistry and biology labs are becoming more and more automated. Therefore, they are less energy intensive. And there is this spectrum of lab spaces in terms of intensity and energy use. So the chemistry lab with highest intensity is on one side, and we have this other kind of general science and analytical science kinds of lab that are on the sort of dry side of the spectrum. With integrated planning, the architectural team works closely with the mechanical team to understand how many of each is needed and at the very beginning of the project. And that's, we think, where the sort of overall science trend is going. We're moving away from producing data to analyzing them. So again, more of the sort of general science and analytical science type of labs. And with more labs falling into the dry and damp category, the spaces inherently use less energy. If the mechanical engineers work with the planners and design according to the real needs, there will be a big cost saving in the mechanical scope. With this approach, we save a significant portion of the cost that otherwise would have been spent on an over-designed infrastructure. So now these freed resources can be reallocated to other new requirements that we discuss in this section. The real bottom line is that lab project budget structure has not changed, but the expectations of lab and program has changed. And integrated planning allows for creative budget reallocation to achieve these new project goals. This image is from one of our tenant lab building projects. The team worked really closely with the owner to understand their needs at the beginning of the project. All the trends that we talked about earlier were part of the performance requirements for this innovation park. The diagram on the screen is an example of how we've worked with the engineers to differentiate spaces in terms of energy use intensity and yet provide flexibility that was needed for the sort of tenant lab space. As you see, there is a gradient of spaces from public to dry lab and then wet labs with separate mechanical feeds. This helped to save mechanical costs and add other features to the building, like this central atrium that really energized the building. This project has an integrated delivery method, or what we call IPD. So integrated project delivery is really the natural landscape for this value design and integrated thinking that we are advocating. The main tools in IPD that foster integrated plannings are the way the relationships are set up in an IPD environment, and sort of the tangible incentives that are in place that promote close collaboration. And the first two, in our experience, result in a positive behavior change. In design, bid build, construction management, or P3 project delivery, the relationships are hierarchical and often the interests are adversarial, not all, but some at least. In IPD, even the trades, only the major trades identified by the team are at the planning table in the big room setting. They also understand the project goals and have a say in them. So this arrangement in itself sets up the team to work and collaborate differently. And the financial structure of the IPD also promotes collaboration. In integrated project delivery, the target performance and target costs are set up at the planning and conceptual design phase by all the stakeholders based on the project goals and the client's budget. A profit margin is also identified, and then you see that value is overlaid on this diagram. If the team and the solutions don't work the way they are supposed to work, in other words, the project is over budget, they start to eat away from their profit because they have committed to sort of this target performance. And on the other hand, the more integrated they plan and design the building to do more with less, they increase their profit, which is this surplus value that you see in the diagram. The combination of integrated process and incentive structure really pushes all the team members toward value-based decision-making. It really encourages parties to focus on the project outcome rather than their own individual goals. In one of our lab IPD projects, there was a dilemma between using a steel structure versus mass timber for a portion of the building. After a thorough cost estimate and considering all the implications, the team realized it's actually cheaper and more valuable to use mass timber. It was an interesting breakthrough moment when the steel trade, as part of the poly-party agreement, actually announced it to the entire big room and effectively left the project. IPD really benefits from the early and timely contribution of knowledge and expertise, and the key is the integrated planning process. It allows the team members to realize their highest potentials while constantly expanding the value they add to the project, and the team's success is tangibly tied to the project's success, shared risk, and rewards. And the outcome is the opportunity to design, build, and operate as efficiently as possible. We understand that we don't always have the opportunity to do integrated project delivery, but we can borrow some IPD principles for other delivery methods. These are some of those principles: early contribution of knowledge and expertise, effective and early participation in the planning, value-based decision-making, and last but not least, the team's success should really be tied to the project success. So the background image is the York University project that we talked about. This is a CM delivery, but our team has adopted these IPD principles to maximize the value for the project. Thanks everyone for listening. I'll be happy to answer questions.
Well, thank you so much, Samaya. That was very interesting. For questions from panelists, we can either put them in the chat or ideally in the question and answer, at which point I can kind of read them out and we can all discuss. I had one while everybody else thinks of one, Samaya. So yeah. As a vendor, how do you approach the team, the IPD team, in the best way to give the best value? I mean, coming in across with recommendations and everything else you've been talking about.
So for the IPD process, what happens is that at the beginning of the project, actually the team, which is typically includes the architects, the main consultants, and the contractor, they select major trades for the project and they bring them officially on board from the get-go. So the trades are at the table when the design is evolving and some of the decisions are made. And in a non-IPD environment, for example, in the York project, which is a CM, the CM is inviting some trades to provide design assist early on. So, and their input is really helpful for our project. They sort of made us to rethink some of the solutions with what we understood from their input.
Okay. Oh, and then we've got one here from Stephen. And can you see that, Samaya?
Just give me a second, not yet. Is that in the QA? Can you read me?
In the QA.
Okay. Yeah,
I can read it to you. So Stephen asks, to what degree was the facilities operations team involved in the design IPD process, and how much consideration was taken in terms on ongoing operational costs when value engineering versus just reducing initial construction?
Very good question. So when we do IPD project, the owner is an active participant of the whole process. So they are in the big room with everyone else. So they basically facility team and maintenance team are part of the sort of owners group. So they are always there and they provide input. And always the sort of the operation aspect is part of the discussion and decision making. So it's actually one of the benefit of IPD that now, because we are not only focused on the sort of short-term goals and just the construction budget, but oftentimes even the operation budget, client open it to the team. So those that aspect can be considered as well.
Okay. And then we've got another one from an anonymous attendee. On the mechanical side, what strategies were used to reduce capital cost? Was there anything else besides the pieces you spoke to?
There were other items, but the major one was sort of this shift from under chilled beams to under floor air distribution, and this was for the sort of more dry and damp spaces. But for the wet labs, basically we use air quality system to lower the air exchange rate where it's not necessary. One other thing that I can remember was that, for example, where it was possible with the program, we would put fume hoods in more enclosed spaces rather than open, lab spaces to just limit the footprint of sort of the most intense spaces as much as possible. That makes sense.
Yes. And then from Sambos, he just states that there was an excellent presentation, especially the illustration of value in laboratory planning and design. He is curious how the placement of laboratories in the partial basement worked for bringing in daylight into the labs, and what were the conversations regarding adjacency of these labs to the research offices, in line with the structure of interdisciplinary research spaces.
Yeah, this project, York University, this it is for a sort of education purposes. So they wanted to give access to the wet lab spaces to only certain students. So they wanted that kind of separation, but there are some sort of administration and dry lab spaces as part of the lower level as well. But because the site has a topography, there are two sides of that floor that has sort of it's kind of exposed and has windows. So we just try to plan to put more of the sort of more public and accessible spaces in those edges of the building.
And then there is another question here from Justin Purdue. In terms of the integrated design process around labs, where do you feel the greatest gains will be made in the future, like architectural, engineering, estimation, construction?
Sorry, I missed part of that question. Can you say that again?
Sure. In terms of the integrated design process around labs, where do you feel the greatest gains will be made in the future? As an example, architectural, engineering, estimation, construction.
I think the biggest gain is really about understanding that this sort of most intense lab footprint is shrinking. And I think if the mechanical and electrical engineers and architectural sort of discipline, they work really together, they can do that kind of differentiation between the spaces that are more intense versus less, and that helps to save energy but also save mechanical costs and reallocate that sort of saved budget and do other things that we need to do. I hope I answered the question.
And then we've got one here. Again, thanking you for a great presentation. They have a question about project quality. When the budget is set at the beginning of the project, how do you ensure that the quality is not compromised when all partners are trying to get the incentives at the end?
Well, I'm not sure if this question is related to IPD or non-IPD project. Well, if it's a non-IPD project, typically those qualities or, performances are part of the program that we receive or the programming exercise or visioning that we do with the client, right? So they have certain ones that they can't really compromise and need to achieve, and there are others that are more of wish list items. So basically, we try to achieve as much as possible, right? In the IPD settings, those performance goals, there are some basics that are communicated to the team by the owner at the beginning, but also the team goes through a pre-validation process that really sort of do a conceptual design against the budget, and then set some of those target performances together as a team with the owner. And they sort of become these official target performances that the team cannot compromise later on. So it's a very kind of integrated and collaborative way to set those goals.
Okay, if there are any other questions, and while we just wait to see if there are any more, just a quick reminder that this was a recorded presentation. It will be able to be found on the SLCAN website for members once you log in, so that you can come back and re-look at it, which I know I'm going to do because there was a bunch of fantastic information in here. Thank you again, Samaya, for presenting it and pulling this together. I'd also like to remind everybody that next month we're going to have another webinar. In this case, it's going to be a data-driven approach to healthy and safe lab management. Are there any other questions? It doesn't look like it. So if that is it, then I will let everybody go. And once again, just thanks, Samaya, for just a fantastic presentation. And thank you, members, for attending.
Thank you for all the questions and for hosting this.
Perfect. Thank you so much, and everybody have a wonderful day.
Thank you.